Hello, and this is the final module for the week. Remember, next week we have an exam on Wednesday. I'll just send it out to you. You have 24 hours to hand it back in. So that will cover from variation of parameters to today's section. So that's 3.4.2 to 4.1. Okay. Now we're doing an introduction to first order systems, and in particular first order linear systems. So why do we want to do that? Well, lots of problems have more than one dependent variable. So like if you're a biologist and you're studying predator-prey models, or you're a military person and you're studying battle and you've got two sides, blue versus gray, you need a system. We've already seen that any differential equation can be written as a system of first order equations. So really talking about systems of first order equations is the same thing as talking about differential equations. We've kind of seen that the way that you solve differential equations is by using systems. So like the way that you solve a high order equation is by writing it as a system of first order equations. Big reason is we can use linear algebra, and that's really, really powerful. That can really solve a lot of problems. And then later when we get to chapter 5, we can see that we can use the phase plane to give us a lot of information about what the system does. Okay, so a standard thing we've done is to have a standard form for our equations. So standard form for an n-dimensional system of first order differential equations is the following. So we've got n equations with n dependent variables plus 1 independent variables. So f1 through fn are functions of those n dependent variables plus t. Okay. So let's have a look at an example of that. So here is a third order equation, x triple prime plus 4x double prime plus 3x equals 2 plus t. So this is a three-dimensional system. It's a non-homogeneous system, and it's a linear system. Okay, so the way that we turn it into a system is we need three variables because it's three-dimensional. So we're going to have x, x prime, and x double prime as our three dependent variables. It's a third order equation. We've got x triple prime, so we only need to go up to x double prime. And then the system is x1 prime equals x2, x2 prime equals x3, and x3 prime is minus 4x3 minus 3x1 plus 2 plus t. And that's how you convert a higher order equation into a system, right? So the first one, there's always going to be something like x1 prime equals x2, x2 prime equals x3, x3 prime equals x4 if it was like a fourth order equation, whatever. So you get those out of the way. And then the last one is kind of giving us the equation. Okay, the next one here, we've got a two-dimensional problem. It's linear and it's homogeneous, right? Because there's no non-dependent variable terms in there. So it's very easy. We let x1 be x, x2 be y, and then x1 prime equals 2 and x2 prime equals minus x1. Just basically redo the equations. Things can get more complicated. So here, for example, we've got two equations, a first order equation and a third order equation. So together they make a four-dimensional system. X only goes up to x prime, so we only need x1 for the x variables. y goes up to y triple prime, so we need 3 variables for that, so we'll let x2 be y, x3 be y prime, and x4 be y double prime. And then we just write down there. And we see that it is 4-dimensional. It is non-linear, right? Because we've got the xy term in there and we've got the y squared term in there. It's because it's the dependent, it's got to be linear in the dependent terms. And it's homogeneous, right? Because there's nothing that's not a dependent variable. Okay, and so we can just write out the system like that. Sometimes you need to do even more work. So for example, here we've got, if you look at it closely, we've got 2 dependent variables, and it's not in standard form. So we want to write it as a system. So this is going to be a 2-dimensional problem. It's 2-dimensional system. It's going to be linear, right? We see that all the terms are linear, and it's going to be homogeneous. So to be able to go anywhere, we've got to actually solve for x prime and y prime. And so that's pretty easy, because you see what you have to do is, what do we do? If we want to solve for x prime, for instance, or solving for y prime is probably easier. So if we add those 2 equations together, we get something. And so we can solve that to get x prime equals 5x minus 7y, y prime equals 3x minus 2y. If we go ahead and just solve those system of equations. So once we've done that, we've done all the work, right? So we just let x1 be x and x2 be y, and then we can just write down the system. Okay, so the module question for this module that I'd like you to hand in anytime Monday is, here we have a equations x double prime equals x plus y, y prime equals 5x. Write it as a system in standard form. Figure out its dimension. Is it a linear system? Is it a homogeneous system? Okay. So that's systems in general. What we're going to be concentrating on is linear systems. So again, what's the standard form for this? So a standard form for an n-dimensional linear system of first order differential equations is what you see there. So instead of having general functions f1, f2, etc., we see that all the x1 through xn, it's all linear in those terms there. And so we've got these coefficients aij, where I and j go from 1 to n, and bi, where I goes from 1 to n. They can be functions of t, right? So it's still linear if it's, x1 prime equals tx1 plus sine tx2 plus blah, 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 okay? But you notice it definitely is a linear system, because you can see the matrix in there, right? The aij gives us a matrix, okay? So it's got n dependent variables, that's why it's n-dimensional, okay? And it's non-homogeneous if any of the bi's are non-zero. And if all the bi's are 0, then it's a homogeneous system. Okay, so let's do a nice juicy example, a double spring mass system. So there's lots of these out there. There's lots of different ways that you can connect different masses with different springs and anchor them to points and let them vibrate and see what happens. So it's a much more complicated story than the simple spring mass system we saw earlier. So we've got 2 springs connected to 2 masses, as in the diagram. I'm going to assume that the spring constants are the same, just call that K, that the masses are the same, call that M. Let's have no damping, so it's a frictionless surface. And so x1 and x2 give their displacement from their equilibrium position. So at the moment, let's assume that it's in equilibrium, then x1 is 0 and x2 is 0. And the positive direction is the right. Okay, so we've got to figure out what the equations are. And so this is just a simple adding up of forces, right? The force exerted by the first spring is K1 times X1. The force exerted by the second spring is K2 times X2 minus X1, right? Because if X1 moves, if X1 equals X2, then that second spring isn't compressed or stretched at all. So from that, the force exerted on the first mass, right, is we've got to add those two forces of the two springs together. It's minus kx1 plus k times x2 minus x1. You just have to get the signs right to see, the first spring is on the left, so it's pushing in that direction. The second spring is on the right, so it's going to push it in the positive direction. And the first force exerted on the second mass is minus k times x2 minus x1. Okay. And so this gives us a nice four-dimensional homogeneous linear system. Okay, we've got x1 and x2. Since we're dealing with second derivatives, we need x3 and x4 for the derivatives of x1 and x2. And the equations, we just then solve for x1 prime, x2 prime, x3 prime, x4 prime. The interesting one, of course, is for x3 prime and x4 prime. For x3 prime, we have x2 minus 2x1, because we're adding up what's happening with the springs. And for x4, we've got x1 minus x2 in there. Okay, and that's it. Thank you.